All right. Hey, everybody. Welcome back. So in this video, we want to continue exploring this thing that we saw last time, this object called a Taylor polynomial. And what we saw at the end of last class is that a Taylor polynomial tends to look a lot like our function that it is, I'll say, approximating, right? So a Taylor polynomial will look a lot like a given function to the point where it looks like it's a nice approximation of a function. And sometimes we'll talk about a Taylor approximation when we're talking about a Taylor polynomial. So our goals for this video are to explore this relationship a little bit by discussing something called Taylor's theorem. Taylor is the mathematician who first really explored Taylor polynomials in great detail, or at least the one whose name is attached to everything. So we'll discuss Taylor's theorem, and we'll discuss what we talk about in terms of a remainder or an error of a Taylor polynomial. Okay, now I want to pick up where we left off last time, which was looking at the sine function, right, sine of x, and looking at different Taylor approximations or Taylor polynomials for sine of x. So we had our linear approximation, that was just g of x equals x. We had our third order Taylor approximation, our fifth order Taylor approximation, and so on. And what we sort of see, right, or at least we sort of intuitively get, is that these Taylor polynomials, if I have a higher order, right, so a higher degree, I get a better large approximation for my function sine of x, right? So here in this picture, I have my nth order polynomial or my nth degree polynomial, and we can see that it is actually approximating sine of x reasonably closely, at least from, say, negative pi to pi. To zoom in a little bit, let me choose one that's a little more manageable. Let's focus on this fifth order Taylor polynomial. Right, again, this is a polynomial that we said is centered at 0, Taylor polynomial centered at 0, aka a Maclaurin polynomial. And so we see that at 0, this purple function is a really, really, really good fit for the sine function, right? We can see that here's our function sine of x, here's our polynomial, and they tend to look really, really close to being identical near 0. As I get further away, we see ultimately that this is not, or that close approximation fit does not hold forever. By the time we get to, say, x equals 4, there's a pretty big difference. By the time we get to x equals 6, our polynomial is already off the screen, right? And so there's a big difference between the two functions out here. Still a pretty big difference here. But by the time I get into, say, less than x equals 2 or greater than x equals negative 2, it's a pretty good fit. It's not a perfect fit, though, because if we zoom in, right, what we see is that there's still some difference between the two functions. And even if I were to zoom in, let's say, right around here, oh, man, I chose a poor spot for illustrate. Ah, there it is, yes. Notice, even if we zoom in a place where it looks like a good fit on one scale, we can see that there is still a tiny little difference between the two. Right? So a really interesting feature about our Taylor polynomial is that it is a perfect fit, right, in that the functions align at x equals 0, but everywhere else there's probably going to be a little bit of a remainder or a little bit of an error. And that question of how big is the error, for what x values is this a good fit, and for what x values is this not a good fit, that is a question that we want to explore in greater detail. Okay, so we want to make some definitions here that will help us, I guess, go forward and discuss these things more quantitatively. We want to define the remainder of our function at a given x value, right? So as we saw in our previous picture, our remainder might be really big at x equals 6, or our error might be really big at x equals 6, but might be reasonably small at x equals 2. So we want to be able to talk about this error or this remainder at different x values. And so we have the following definition. So for a function f of x, the nth remainder for f of x at a specific x value, x equals c, is given by the function r sub n of x, which we are defining to just be f of x minus the polynomial p sub n of x. Okay, and I said, because I said this is at x equals c, I should probably say this is r sub n of c equals f of c minus p sub n of c. But you see that this remainder can be described as a function. And indeed, this is really the function that makes the most sense, right? This remainder is being described as the difference between the function itself and the polynomial. Another equivalent way that we can think of this is that our original function f of x, in our example, the sine function, can be constructed with our polynomial, nth order Taylor polynomial, plus some additional remainder, plus whatever is left over. And so we're defining this r sub n of x as the difference between these two. Now, our polynomial, our Taylor polynomial, can sit above the original function or below the original function. And so if I'm describing error, I will typically take my error to just be the absolute value of this remainder, right? The remainder can either be positive or negative. If I take the absolute value, I get a positive expression, which I can use to identify this error. And so our big question is, how big can this error get? And can I have an estimate on what this error is? And it turns out the answer is yes. We can rigorously come up with a good estimate for what this error is using something called Taylor's theorem. Now, we won't typically apply Taylor's theorem directly, but we'll use it to calculate the error or calculate a bound on the error. So Taylor's theorem gives us an explicit formula for calculating that remainder term, right? And so we can use Taylor's theorem to calculate the remainder. And Taylor's theorem says if our n plus 1th derivative of our function exists, right? So this meant n plus 1st or n plus 1th derivative of f. So if that exists and is continuous, then I can rigorously define the remainder as, or then it turns out that the remainder is exactly equal to this expression. And this is sort of a weird expression, so let's unpack this a little bit. First, we have 1 over n factorial, and then we have this area accumulation function, right? So this is really expressed, it's an integral involving an upper bound of x, lower bound of a, right? This was where our Taylor approximation or our Taylor polynomial was centered. And then we integrate x minus u to the n times the n plus 1th derivative of f at u, and we integrate that with respect to u. So because this is an integral with respect to u, and we're integrating from some fixed constant up to x, this is really a function of x, right? So this is a function of x, and as we've seen, right back in Calc 1, we can construct these weird area accumulation functions, these functions of x's, by integrating up, another function. So this is a function defined as the integral, or the area accumulation of this function in here. Now, this is a little weird and hard to work with, as you can imagine, right? An integral of a polynomial times an n plus 1th derivative of our function. But Taylor's theorem guarantees that this is explicitly what our remainder is equal to. And so the way that we use this in practice is actually as follows. What we do is we check. We either assume it's true or we check to make sure it's true. We make sure that on a given interval, we check to make sure that the n plus 1th derivative of f is bounded. In other words, that derivative does not get too big, or even if it gets really big, that's okay. But we still make sure that it's less than or equal to some value m, right? And the key to what will ultimately be our error estimate is trying to figure out what this m value is. So if on an interval, our derivative doesn't get bigger than a number m, then I can do the following, right? I can, first of all, throw absolute values on everything. That doesn't change anything, right? I guess on the left-hand side, this now gives us the error. On this right-hand side, the absolute value signs are just giving us a slightly different expression. But I can make the observation that if this is always less than or equal to m, if this is always less than or equal to m, then this expression over here, I can convert this weird piece to an m and throw in these absolute values here, right? Because I am only, I guess I should say because this was always less than or equal to m, this piece will always be less than or equal to m, and that's true at every point in this integral, so that's true over the entire integral. And so that actually gives us the expression that this left-hand side, right, so the error is going to be less than or equal to, we have 1 over n factorial, and now I can pull that constant m outside of the integral, and this just becomes the integral from a to x of x minus u to the n du. I should say with absolute values still in there, right? So we still need those absolute values. Well, now this becomes something that we actually can hope to integrate, right? So we have 1 over n factorial, we have this m, and then what we have over here is going to be x minus u to the n plus 1 divided by n plus 1. And now, because we're integrating du, right, there should be an extra negative sign in here, but the extra negative sign will get canceled out by these absolute value signs. So we end up with this evaluated when u equals a to u equals x. I guess I should still have absolute value signs in here. And so what we're going to get is when x is equal, when we plug in u equals x, this will just become a 0. When we plug in u equals a, we will get an x minus a to the n plus 1. We're still dividing by n plus 1. The absolute value signs make all of this positive, and we end up with 1 over n factorial times m times x minus a to the n plus 1 divided by n plus 1. So slightly complicated expression. We can simplify this a little bit, and we'll do this on the next slide by taking the n plus 1 in the denominator over here and moving it into this denominator. N factorial times n plus 1 will just be n plus 1 factorial. So we can consolidate that. And so what we'll get is the following error bound, right? So the error of our polynomial, as calculated on the other page, is going to be this capital M, an n plus 1 in the denominator, rather an n plus 1 factorial in the denominator. And in the numerator, it'll be this expression x minus a raised to the n plus 1. Here we're evaluating it at a point c, so it becomes c minus a to the n plus 1. Okay, and that is true assuming that the n plus 1th derivative exists and is continuous, and that we have this bound for all values in between a and c. So what are some tangible takeaways here? This will be our, I should say, this is our error theorem, right? Or this is our error bound, our formula. So this expression on the left is just the error of our Taylor approximation at x equals c. And what we see typically is that, well, let's see, what we can notice is at a, right? Let's make some tangible takeaways. At x equals a, or at c equals a, yeah, at x equals a, this expression over here just becomes a minus a. And so this entire expression becomes 0. So at x equals a, the error equals 0. This is what we hoped, right? This is what we expected because our Taylor polynomial and our original function are set up in such a way that they agree, or maybe put in a better way, our Taylor polynomial is constructed to agree with the function at x equals a. Second takeaway message, as n increases, our error typically decreases. Right, at a fixed c value. Right, this is a little trickier to show because as our n increases, that means we're taking a higher order Taylor polynomial. This m value might change, right? The m value might change up here. But what we see is that ultimately this denominator, this n plus 1 factorial, gets bigger and bigger and bigger, forcing that entire expression typically to get smaller and smaller and smaller. So as n increases, error typically decreases at a fixed c value. And then our third takeaway is that at a fixed n value, error typically increases, as we get further away. So as c is further from a. Right, and that we can see because, right, so at a fixed n value, this number is fixed, that exponent is fixed. But as we get further away, so as our c values are allowed to range further away from a, this difference gets bigger, which means that the numerator of this side of the equation is getting bigger and bigger. And it's potentially the fact that our m will get bigger, right? Because as we get further away from a, our n plus 1th derivative might get bigger. So we might have to raise our bound, raise our m. So both of those stand to potentially increase this this right-hand side, which means that this left-hand side can increase as well. So 3 tangible takeaways here. Okay, and again, we see all 3 of those tangible takeaways, right? We see all 3 of those here in this picture, right? In particular, we see that at a, our polynomial completely agrees with the function, right? So at a, the error is 0, or in this case, a equals 0. So at 0, the error is 0. As we increase our n values, our errors typically decrease. Let's look at, say, x equals 3 here, right? For small values of n, that's a big error. But as n increases, that error, right, the absolute value of the difference, gets smaller and smaller and smaller, right? So that error typically decreases. And then finally, for a fixed value, right, so a fixed n value, here let's say the 5th degree Taylor polynomial, as I get further and further away from 0, my error has the potential to get bigger and bigger and bigger, and we see that as well. So that's going to do it for this video. Thanks so much for watching, and I'll see you next time.